Good morning, everyone. First, I think people coming from outside, welcome to IIT Tirupati. So, thanks for joining us on this GIAN course on high-speed flows theory and measurements in jet engines. We have with us Professor Lionel C. Ganipa from Brunel University, London. So, along with him, I'll be delivering couple of, I'm Dr. Madan, so we'll be delivering few lectures. So just to give a little brief about Professor Lionel, so he did his PhD from Chalmers University, Sweden, on optical diagnostics, and then after that he did postdoc at Radboud University, Netherlands. Then after that he joined Brunel University, London. He has been there for about 20 years, right, sir? 20 years. He's right now he's a professor at Brunel University, London, Department of Aerospace and Mechanical Engineering, and Center for Engineering and Physical Design System. Yeah, I just work. So, yeah, I worked with him at Brunel as a postdoc. He works on alternative fuels, optical diagnostics, and other things. He has done a lot of projects, EPSRC funded projects. Yeah, so to give about the course, first let's welcome Professor Lionel to IIT Tirupati.
Thank you.
So about the course, we have so for starting from now, so we'll have sessions till Friday afternoon. So first 2 days it will be mostly a theory, so you'll have a classroom lectures, and third day, that is Wednesday onwards, Wednesday, Thursday morning we'll have sessions here. Afternoon we'll go to lab, so where you will have a chance to see some of the demonstration, mainly optical diagnostics used for that, particle image velocimetry, Schlieren and shadow imaging. Friday also we'll see the setup. If we can do some high-speed backlight imaging setup, we'll try to arrange here. Otherwise, Friday morning also we have a session, followed by a small examination, so which is a part of the GIAN course. So by Friday afternoon, we'll be wrapping up. So let's start the session today. So thank you, sir, for accepting our invitation. And
yeah, that's good. Yeah, it's always a pleasure to work with you.
Thank you, sir.
Yeah. Okay.
So we'll give to
okay. Thank you, Madan, and thank you for each and every one of you who have come, either as a student or from a visitor, to attend this course. As Madan mentioned that I'm at Brunel University of London, so here you can see that the campus still, it's a lot of green belt in London. Let me give you some indication. So you see this is the indoor athletic center. This is the place where Usain Bolt used to practice for the London 2012 Olympics. And this is what we call as the Howell building. This is where my office is. This is where the place where me and Dr. Madan used to meet often to discuss about our research work. And surrounding this Howell building, there are towers, which is Tower A here, and then B and C and D. And our labs are based in, most of our labs are based in towers. Mechanical are in Tower B and also in Tower C. So this is just to give a brief idea about the campus, and not very far from Heathrow. So just to say a few words about Brunel, the College of Engineering, Design and Physical Sciences. About 140 academic staff, 1,500 undergraduate students, 700 postgraduate students, about 120 doctoral researchers, 35 administrative staff, and 40 technical staff. I'm placed within the College of Engineering Design. I'm placed in the Department of Mechanical and Aerospace Engineering, Mechanical and Aerospace Engineering Department. Within the department, there are various research centers. I'm part of the Advanced Powertrains and Fuels Research, which is a very large group with very eminent academics in that area, working in the area of all of us, working 5 to 6 people there, working in the area of engines and fuels and combustion. And it is one of the UK's leading and one of the largest and well-known engine research centers at Brunel University. Looking at my own area, I focus on alternative fuels and sprays and combustion aspects of it, and emission and soot. Just to give a small setup of the whole lab, I just put up some of the clips of Dr. Madan's experimental. You find this in his paper, which is well cited. It is cited. Yeah, it's a very highly cited paper which we did together at this point. So if you have to do any work on fuels, then basically you need to have fuel here. So you have the fuel. So you need to have a temperature here, and you have an imaging device, and you have an illumination source. So this is a simple setup. So we have a number of setups with high pressure or reciprocating engines, or maybe a fundamental levels, or maybe as a jet setups also. So that's the background about Brunel and what I'm doing there at Brunel. So let's go back to the course itself, high-speed flow theory and measurements in jet engines. Often myself and Dr. Madan, always we discuss about various research aspects, and this came up, and then we thought we'll propose something on this. The topics that will be covered is just given there. We look at the overview of the gas turbine propulsion systems this morning, where we look at the turbojet, turbofan, turboprop, turboshaft, not in detail, just give an overview of it. And then we look into, this afternoon, we look into the combustion in supersonic and hypersonic engines based on the Rayleigh flow theory. And in the course, we'll also cover the shocks, shock waves, and application of shocks in supersonic inlets. We also look at the nozzle flow under supersonic conditions. Also, we'll look at ramjet and scramjet, and then the major part of it is also measurements, where we look at the various optical measuring devices, measuring techniques in this course. So this is the typical content of this course. Okay, now let's go into today's topic. It is the overview of gas turbine engines used in aircraft propulsion. So let's start with the basic principle of propulsion. What is propulsion? It could mean different things for people in different areas of their research. If you look at people in the sea, for them it's a marine propulsion. If people on the road, it's a propulsion on the vehicles on the road. And if it's people on the air, it is aircraft propulsion. Basic principle is that moving forward. That is the basic idea behind it. It is based on the Newton's third law, which says every action has an equal and opposite reaction. The simplest example is you take a balloon, blow all your energy into it, you fill it up with the air, you hold the mouth of it. Now there's air at high pressure inside the balloon. It's perfectly balanced with the larger surface area of the balloon, but then when you release the mouth of the balloon, so you can see that it is moving forward. So the action is the expelling of the air, and the reaction is moving forward. So in aerospace applications, action is accomplished by burning fuel with air to increase the pressure and temperature, which then expands to cause a jet. So the reaction to this action is the thrust force that is causing the aircraft to propel forward. Okay, so this is the basic principle of propulsion. Now if you look at the classification of aircraft propulsion, basically you can classify them into two: air-breathing propulsions and non-air-breathing propulsions. And I need not tell anything about rockets, because Sriharikota is not very far from your place. You're pioneers on rocket launching, but for this course we are going to look only at the air-breathing engines. Until 1940, people were fighting, oh, we need to have a two-stroke engine, we need to have a four-stroke engine, no, we need to have an air-cooled engine, we need to have a water-cooled engine, we need to have a rotary engine. Much of the research was focused on reciprocating internal combustion engines since 1940. Since 1940, the gas turbine developed, jet propulsion starts picking up, and not much talk is there, but still there are few of the aircrafts with reciprocating engines for training purposes. So we will be focusing more on the jet propulsion engines. Within that, we'll be looking at the gas turbine based propulsion today, and then we will look at ramjet, scramjet. If time permits, we'll look at the turbo ramjet also. Okay, so this is the overview which we'll be covering this morning. Starting with a turbojet engine, it's a T38. What you see there, and it's a twin turbojet engine. Second one is the commercial aircraft with a turbofan engine, and then also commercial as well as military application turboprop, and then you have the turboshaft engine here. So let's look at the turbojet engine. So before we even look at it, let's okay, I think I need to sit, it's too much bending here. Okay, so let's start with a turbojet engine here. The basic fundamental aspect of a jet engine is the gas generator, which means it has three main components. One is the compressor, which is driven by the turbine. So the compressor is coupled to the turbine. The turbine gets its power and energy from the burning of the fuel in the combustor. So this is the cut section view of it. It's a very simple schematic, and this is basically what we call as a gas generator. Now you need to size these components. Now this sizing of these components, depending on what is the design Mach number, what's the design speed at which you want to fly the aircraft, what is the gross takeoff weight you want to lift the aircraft, what is the transonic acceleration, how quickly you want to avoid this, if you're going to go from Mach 0.9 to 1.1 or 1.2. So that's what we mean by transonic acceleration. So depending on that, then we define what is the pressure ratio of the compressor, what is the adiabatic efficiency of the compressor, what is the amount of fuel that is to be injected into the burner, what is the air to fuel ratio in the combustor, what type of thermal barrier coating that we need to apply onto the combustor, what is the thermal limit, which is denoted by tau suffix lambda, what is the maximum temperature up to which the combustor can operate, and what will be the pressure ratio across the turbine, and what is the adiabatic efficiency of the turbine. And I can keep on going because they are made up of, again, number of stages into it. So what is the stage efficiency, number of blades, and blade profile. So this is the fundamental aspect of it. This is called the gas generator. Now if I add an inlet to it, and if I add a nozzle to it, this becomes a simple turbojet engine. So here is the inlet, and here is the compressor. Were you able to see what I was writing out? It disappeared. So this is the inlet. So this is the, I don't know, simple turbojet engine. So here is the nozzle here. So the standard aerospace recommended practice is that this is the atmospheric environment at which the aircraft is flying. See, unperturbed condition, 0. Inlet lip, here is the front of the compressor. So exit of the compressor and to the inlet to the combustor. Exit of the combustor and inlet to the turbine. And here is the exit of the turbine 5. Now, as I did mention, this is a simple turbojet engine, which we are going to develop this further. So there will be some components coming between 5 and the exit 1, 9. So, which means that an aircraft is flying at a flight static conditions. The pressure will be P naught, the temperature will be T naught, the density will be rho naught, and the velocity will be V naught, the corresponding Mach number will be M naught. So when the air enters into the engine, now you can see that the function of the inlet is to decelerate the flow. We are now looking at a subsonic flow. The flow enters into a diverging geometry. So as the flow enters into this engine, now what will happen? The velocity decreases. What is the effect of a decrease in velocity? When I talk about velocity, there is a kinetic energy associated with it, specific kinetic energy associated with it. The kinetic energy here, at this point here, kinetic energy decreases. Here this where the principle of conservation of energy comes into picture. The energy decreases in one form and it disappears, but it will reappear in some other form, which will cause the pressure to increase. So that is the main function of the inlet. The inlet is to decelerate the flow, make use of that kinetic energy, and to increase the pressure. And the whole objective is to improve the efficiency of the whole combustion process. We need to have high pressure into the system. So you increase the pressure. At the same time, we need to make sure that we need to minimize the ruffles. So that is the main function of the inlet. And then the air will pass through the compressor based on the pressure ratio of the compressor, which is again designed based on the flight speed. As a rule of thumb, faster you go, you don't need to have high pressure ratio because you get the ramming effect there. So then based on the pressure ratio of the compressor, you increase the pressure and you feed that high pressure air into the combustor where fuel is injected, and fuel and air is mixed into the combustor and it is burned to high temperature. That temperature, maximum temperature, is the limiting because it is to be operated at a certain limit, beyond which it is good to have high temperature, but the limitation is the material limitation. And so we have this thermal barrier coating into these combustors. The high temperature burned gases will expand to the turbine, and that turbine will produce some work. The work that is being produced by the turbine is used to drive the compressor. Now, the amount of energy that is left out will be expelled out of the nozzle, and you have this velocity of gas exiting, or in this case V9, and then you produce the thrust is equal to what is the mass coming in, m dot O plus m dot F. This is the gross thrust that is being produced by the engine. Okay, so this is the basic principle of operation of a turbojet engine. Now let's try to look at it from thermodynamic point of view. So on the y-axis is the enthalpy, on the x-axis is the entropy. As I said, this is the unperturbed free stream condition. The pressure is flight static pressure P naught. Let me represent it on an HS diagram. This is the pressure P naught. So you know these are the isobars going into this direction here. Now it is flying at a certain pressure, environmental pressure, and at a certain temperature. So this is the temperature. So this is the T naught. So when I say enthalpy, which is nothing but CPT, or I can say write it as a T. Cp is constant here in this case, anyhow it's here. So here is the S naught. So these are the initial conditions. This is the flight static condition O. Okay. Now imagine we are not even going into the engine. I'm going to put a pitot static tube outside. So what will happen here? The flow, if I put a pitot static tube in the flow direction, the flow that is coming here at a velocity, let's say this is coming here at Mach 0.8. Eventually, when it approaches the aircraft at the pitot static tube, now the flow will decelerate, which means the kinetic energy is being lost. Eventually, it comes to the point at the tip, the velocity is 0. So at this tip, the velocity is 0. When the velocity is 0, it is referred to the stagnation state. Okay, and this process of flow deceleration could be treated as isentropic. So it's an isentropic stagnation state. So I'm going to plot that point here. So here V naught is equal to 0, and the corresponding pressure is the total pressure, stagnation pressure. So what will happen? The pressure will increase, and eventually I will have this pressure. So this is the PT naught. So there is a relationship between this stagnation pressure to static pressure is equal to 1 plus gamma minus 1 by 2 m naught square power gamma by gamma minus 1. There is also a relationship between dt naught by t naught. This is a relationship between the local property and the stagnation property is equal to 1 plus gamma minus 1 by 2 m naught square. And similarly, you could say for density also. We are not going to look at this 1 by 2 m naught square power 1 by gamma minus 1. So here is the static pressure, and this is the corresponding isentropic stagnation condition, and this is the isentropic stagnation enthalpy HT naught. And one of the things even in real life applications is the inlet is treated as adiabatic. Inlet is treated adiabatic, and also the nozzles are treated as adiabatic. So here it is adiabatic, and here also it is adiabatic. Now this magnitude is the thermal energy, thermal energy H naught at which the flight enters in. So this is the point here. We have this flight entering at Mach m naught. So here is the thermal energy. Now here at this point, this is the kinetic energy, which is half V naught square. So what I am writing here is H naught plus half V naught square, which is the energy balance equation, which is the total energy. That's what I write in here now. Is it clear? So it's H naught plus half V naught square is the total energy. Total energy remains constant here. Now the air enters into the inlet. The air enters into the inlet. So the air enters into the inlet, the static pressure increases, and eventually we have a stagnation pressure here, PT naught. So from here to here, this is the process here. Now as the air passes through the inlet, there is generation of entropy due to losses present in the system, mainly friction effects here. So the entropy increases here, delta S in the inlet. And this is the state T2, because the flow becomes a stagnation at this point, T2. T denotes the total properties of the system. Now here you see this is the loss of pressure in the inlet system. Ideally, if there is no friction, we will follow this path. But because of friction, there is loss. This is the loss. So that is the loss in the inlet delta P, T in the diffuser, inlet diffuser, which is PT naught minus PT2. In other words, this is denoted by another important term, which is called the inlet pressure recovery. So pi d is the inlet pressure recovery. Pi d is PT2 by PT naught. Ideally, we as engineers should be working to pi d to be 1. But because of the losses, pi d is less than 1. So it's be about 0.94 or 0.9 or whatever it is. Okay, so now at this point, air has gone through the inlet, is now about to enter into the compressor. It's going to enter into the compressor. So depending on the pressure ratio, you have this pressure here, PT3 from here, again in the compressor. Actual process will be number of small stages will be there, number of small stages. So this is how the pressure increases in the compressor. Passes through stage, rotor, stator, and the arrangement is there. And so the pressure increases to PT3. That depends on the pressure ratio of the compressor and adiabatic efficiency of the compressor. Now once it has entered into the compressor, it's being pressurized, and then it enters into the combustor where air and fuel is injected. Combustion takes place at constant pressure, but the reality is there will be pressure loss. So here it is PT3, and here this is delta P, total pressure loss in the burner. So somewhere here is T4. So here it is T3, here it is T4. Combustion takes place at constant pressure. This is where the fuel is injected, mass of fuel is injected, and here fuel and air will mix, will form an appropriate mixture, fuel-air mixture, and then it will burn, and then it will increase the temperature, after which it will expand in a turbine. So it expands further in the turbine depending on the expansion ratio of the turbine, and this is the pressure PT5. So here is the pressure PT4, pressure PT5. So this is the state T5, and then whatever energy is left out will be expelled out of the nozzle, and here the expansion takes place to the ambient conditions, flight static P9. So this is the pressure P9. So you can see that it starts with a static pressure, goes to stagnation, then ends up with 1 here. So this is the this nozzle pressure ratio, total pressure ratio across the nozzle. These are all geometrical parameters related with the nozzle, and then it expels out at this particular point with a velocity v9, and from which we can calculate the thrust and so on. So this is the typical cycle diagram of a simple turbojet engine. Okay, now let's look into the development of this simple turbojet engine, because not always we want to operate it like this. At times, suddenly, if Putin wants to attack, then probably you need to escape. So that's what we call as dogfight. Yeah, one aircraft chasing another aircraft. You drop the bomb, and then your adrenaline level goes up. You have to take a steep climb. So in that case, you can't just do this maneuver with this existing engine. So you need to modify the engine, and that is through including a term which is called afterburner. Now, what is an afterburner? Afterburner is a device, as I said here before. Afterburner is a device that could be fitted to this simple turbojet engine so that we can have a thrust augmentation. So if you are going to double the thrust, then the fuel consumption will quadruple. So we can't always use the afterburner. You use it only for very steep climb or in emergency conditions, and then switch it off. Afterburner will have a device which has some casing, outer casing. Okay, this is the outer casing. It has a perforated liner. This is called the perforated liner. And this afterburner also, before the charge enters in, it has a pre-diffuser. So this is the arrangement here. So you can see that diffusing geometry here. The whole idea is to decelerate the flow further down to reduce the velocity so that you could increase the residence time of the charge in the combustor. So this is the pre-diffuser. And then we will have fuel bars or fuel rings. So this is fuel bar or fuel rings to hold the fuel nozzle. Now this will be skirting fuel here. Now we want to make sure that the flame is there in this combustor participating in the combustion. To do that, we need to have something what is called flame holders. Flame holders. And so these are called flame holder. So what's the function of the flame holder? The function of the flame holder is to create a local recirculation zone. So when you create a local recirculation zone, we increase the residence time of the fuel and air to be here mixed burnt, and then it will produce much higher temperature, and then this must be expelled out. To get the benefit, we need to go for a nozzle which is of convergent divergent geometry. So when you have a convergent divergent geometry here, m will be less than 1 as the flow will pass through it, approaches m equal to 1 at the throat, and then it will accelerate it to m greater than 1. So you have the benefit of momentarily boosting, augmenting the thrust to go to high supersonic speeds or low supersonic speeds here. So this is the afterburner. Now where is this afterburner going to be fitted in this engine? Now let's look at this one here. So as we discussed before, so here is the compressor, here is the turbine, and this is the combustor. This is the combustor. This is basically the gas generator, and this will have an inlet. This will have an inlet, and then it is here. This is the shaft that couples the turbine and the compressor. Sometimes this shaft is also called spool, and here is the fuel bar, and this is the afterburner perforated liner in it. And then you have this convergent divergent geometry. So here you can see it is the unperturbed free stream condition. This is the inlet lip, frontal face of the compressor. Here is the end of the compressor, and it's the combustor. Here is the burner. So here, if the mass of fuel is injected, okay, and is burned. Here it is 4, and here it is 5. Now this is the whole afterburner unit is treated as a pipe with a device, afterburner device, and then here is the 7 end of the afterburner combustor. This is the throat area 8, and this is 9. So you can see that a simple turbojet can be modified by including an afterburner. If we include the afterburner, we are able to momentarily increase the thrust. The benefit can be obtained by having a convergent divergent nozzle, which we'll be discussing a bit later on. Now let's look at the cycle diagram for this application. So here is the enthalpy, this is the entropy diagram. So here is the unperturbed free stream conditions. Now you know the details of it. So here is the H naught thermal energy, S naught. Now here is the flight stagnation conditions, PT naught corresponding to T naught. The total energy in the inlet is constant. That is constant. So this is the pressure PT2 at the face of the compressor, state T2. This is the point here, T2. Then the charge will enter into the compressor. It will be pressurized. Here it will be pressure PT3, and here is the state T3. So this is the state here, total state 3. Then in the combustor, this is the actual path through which the combustion takes place. This is the pressure PT4. This is the state T4. In other words, I can say that this is the maximum thermal limit, which is denoted by tau lambda. When I say tau lambda, which is basically what is the enthalpy at this particular point, so tau lambda is HT4 minus H naught. That is the maximum. It's a non-dimensional form. So maximum temperature or cycle temperature or maximum turbine inlet temperature, these are the various terminologies here. Then it will expand in the turbine, to pressure PT5, and here it is T5. Now you can see that we are here at this particular point. So here it is T4 and now it is T5. Now it enters into the afterburner. So here again the fuel is going to be skirted out. So the pressure at the exit is PT7. Now here is the combustion taking place, mass of fuel that is injected in the afterburner. So this is the T7. So you can see that. Again, depending on the combustor properties, whether you can go up to this level or we can keep it to the same level as the previous combustor, thermal limit. Anyhow, I can just to differentiate it, I can say this is the thermal limit in the afterburner. Then it expands in the convergent divergent nozzle, so you can see that you are able to produce higher thrust here to P9 point here. So this is how the cycle diagram will look like for a simple turbojet with an afterburner. So we've got some fundamental understanding now. So now let's go into the real applications of it. So this is the inlet. The screen has changed now, yeah? Are you able to see? So here is the inlet. This is the part of the inlet here. So all the process what I have explained, the physics is happening here. The kinetic energy is utilized to increase the pressure. And then you see this compressor. The compressor which is closer to the compressor is normally called this high pressure compressor, and the turbine which is closer to the combustor is called the high pressure turbine. We'll come back to this bit later on also. Now the air that is being pressurized in the inlet, this is the inlet part of it, is being further pressurized in the compressor. So it's an axial flow compressor. So the direction of flow is in this direction. The rotation is there. You have a rotor blade and a stator blade. The rotor will apply the force and increase the pressure, and the stator will be shaped as a diffuser, increase the pressure, change the flow, and feed the flow into the next stage of a rotor and a stator. So that's how it is. So a rotor and a stator comprises one stage. A compressor will have a number of stages, maybe 8 stages, or it can have 2 sets of compressors, low pressure compressor and high pressure compressor. So depending on the number of stages and number of compressors, the pressure ratio will be varied. So the high pressure air that is being pressurized in the compressor further after it's coming from the inlet will enter into the combustor. So this is the combustor. So this is the combustor. And here the fuel is injected and it is mixed here and it is burned to have an optimum fuel air ratio. F is the fuel air ratio, which is the mass of fuel by mass of air. And then the burned gases will be directed to the turbine where you get the power. That power is transferred to the shaft to drive the compressor. The amount of energy that is left out is going to be expelled out in the nozzle. Okay, so now let's look at the general working principle of jet engine. Now air is admitted from the surrounding environment to the front end of the engine, which is the intake. All the blue part is the cold part of it, and the all red is the hot section of it. Now most of the time the function of the inlet is to decelerate whatever the Mach number is. Say let's say if it is 0 as 0.8 0.89 is the flight Mach number, it has to reduce it to Mach 0.4 to 0.5 or 0.6, because most of the modern compressors can handle flow only up to that range. That is the main reason also for having an inlet. Otherwise, it can damage all the blades here. So we decelerate the flow in the inlet such that the Mach number is at the right range so that it could be handled by the compressor. Okay? In the compressor, the charge could be pressurized. Modern compressors can go up to 40-45 times is the pressure ratio. That's what this is the term which I've been using here. So this is a pi c equal to maybe 45 or something. That's the maximum limit. Then the pressurized air enters into the combustor, and the fuel is injected and mixed with the air in the combustor, and again the temperature increases depending on the mixture, fuel, calorific value, all those aspects here. Then the hot gases will expand through the turbine, which extracts and transmits work to the shaft to drive the compressor. Finally, the pressurized hot gases expand the nozzle to produce the thrust. So the schematic what we have explained before is now a bit more clearer here. These turbojet engines are not fuel efficient, so a lot of modifications need to be made to improve it, to make it fuel efficient. But they are still used for defense applications because fuel consumption is not an issue for defense applications. And also it's used for missile applications. So I have explained this process of enthalpy and entropy separately, so now it's much easier for you to understand looking at the global scale here. Now, one of the ways that you can modify a simple turbojet is to augment the thrust is to include an afterburner. So here is this simple turbojet here, and here is the one with the afterburner. So here is the afterburner device. So this is the fuel bar which I have mentioned, so you can see that here. So this is the fuel bar, and this is the ones which will hold the nozzle, and here's the turbine blades. You see this here. Yeah, you can see it here. The turbine blades will direct the air to the afterburner. So the cycle diagram, after it has expanded to PT3, PT4, then it will have a combustion process here in the afterburner, then expansion will take place. This is how the cycle diagram will look like. Understood? So now let's look at the modification of a turbojet engine. Most of the commercial aircrafts, they are really concerned about the consumption of the fuel. They put a lot of fuel tax because they want to make sure that they are fuel efficient. So let's see how the principle of it still has the gas generator. Here is the combustor. Here is the combustor here. So here is the compressor. Here is the burner. Here is the turbine. This is the gas generator. So the principle of going for a turbofan is basically an energy recovery energy recovery process. The energy that is, this is the gas generator. We have seen already this is the gas generator. Any further energy that is left out, energy that could be harvested, is done through incorporating a turbine, which is called the low pressure turbine or a free turbine. Sometimes it is also called the power turbine here. Now you can see that this shaft is of different coupling. It's of different coupling to this one here. Now use this shaft power to drive a fan. Drive a fan, and to place the fan inside a duct. Inside a duct. So you can see that the central core of the jet engine is the gas generator, which is the basic building block. Whatever the energy that is left out is the harvested in the low pressure turbine. So this is the high pressure turbine. So the turbine which is closer to the combustor is high pressure turbine, and the compressor that is close to the combustor burner is high pressure compressor, and so on. So this is the fan. So use this energy from the low pressure turbine to drive the fan. So the station points are as follows. This is the flight static condition, inlet lip, and this is the frontal face of the fan 2, and here it is 3, here it is 4. You treat it as one device. There are different ways to do it, and then here it is 9, in between 4.5, and here it is 13 and 19. These are some of the standard ways through which they are numbered. So the principle is the air is drawn into this. You can see the frontal area is much larger. So when the frontal area is larger, you have a much higher mass of air drawn, so which means it is going to be benefit for the thrust, which is m into v is the thrust. Now so let's look at this one here. So the air is drawn through the inlet, and so here you can see this is the air that is drawn into this inlet here. So I put two colors here. Now the color which is with red is the only mass that enters into the core of the engine to the high pressure compressor. Just like how it's happening in the turbojet, it is being compressed. Now only a small amount of air is drawn into relatively, so amount of fuel consumption will also be reduced here, and then burnt will expand to the turbine, and still that energy that is left out will be harvested to drive the fan, and then it will expand to this nozzle to produce a thrust. Now that part of the air which is not entering are called, the air that is bypassed is the mass flow of fan, capital F. The fuel is small f, capital F for fan. So this mass is bypassed. So they are pressurized here, and then it enters. Now what you can see here, again there is a nozzle here. This is the thrust. This is the thrust that is produced by the fan nozzle. Here the thrust is produced by the core nozzle. So this is hot, this is cold. But nevertheless, you are going to get the thrust from this. So here the velocity is V19. So we are going to get a velocity coming out. Here it is V9. So when we look at the thrust comes from the fan nozzle plus thrust comes from the core nozzle. Because you're not going to add any fuel to this green part of the air that is being bypassed, the engine becomes a bit more silent compared to turbojet engine. Yeah, so you're not having more energy into it. And then we define a parameter which is called the bypass ratio alpha, which is the mass of air that is bypassed without being participating in the combustion. Bypass ratio. Now all of you understood this one, yes? Now let's try and understand the whole process on an enthalpy entropy diagram here. So here is the unperturbed free stream conditions, which is having the pressure P naught, T naught, S naught, H naught, and M naught, V naught, all of the parameters here. So here is the pressure P naught. Now this is the enthalpy H naught, this is the entropy S naught. This is the state, unperturbed flight static state. From here, the charge enters into the inlet. So here is going from what are the points here? So here it is the pressure PT2. PT2, this is the pressure here. So this is the state T2. So this is happening in the inlet. After which both mass of core, total mass, this is the total mass of air, will pass through the fan, and fan will also have a pressure ratio pi F. Depending on the pressure ratio, we'll be able to increase the pressure up to this point. What is the state point here? PT13, and then this is the T13. Now I'm going to look at the core flow. What will happen to the core flow? The core flow will pass through the compressor, and it will be pressurized to PT3. So this is the T3 in the compressor. This is fan. And then the core flow will pass through the combustor T4. This is the pressure PT4, state point T4. Then it will expand in the, so here is the combustor. Now here is the high pressure turbine, expands here to PT4.5, then again expands further in the low pressure turbine PT5, and then it expands in the nozzle to produce the thrust. So as already mentioned, inlet is adiabatic and nozzle is also adiabatic. So this is the cycle diagram for the charge that enters into the engine and then thereafter passing to the core. But this is not the full picture. The full picture is that there is air which is here at this point. After it has entered into the fan, it is not entering into the core, it is being bypassed, and then it is expanding from this point. Now here you see here P19, T19. So this is the cycle diagram for a turbofan engine. So this is called turbofan Now here it is called unmixed exhaust turbofan engine. The reason why it is called unmixed exhaust is because the air that is being bypassed is not allowed to mix with the burn gas. Red and green are totally isolated. They are not mixed at any point in time. So that is called unmixed exhaust turbofan engine. So this is the now the advantage of this is because they are not mixed, we can go for high bypass. Higher the bypass is much better. You have better, the fuel consumption will be much reduced because you are getting more thrust from the air without participating in combustion. Okay, so that's the benefit of it. So high bypass engines. Now the next concept of the turbofan engine, what I'm going to look at here is that start with the gas generator here. So let me give this one here. It's a turbofan. This is the mixed the exhaust configuration. You don't have much of this in operation now because of some limitations, but nevertheless there are some limited flights which use this. Majority of them use unmixed exhaust. So here is the gas generator. So here is the high pressure compressor. Here is the burner, high pressure turbine, and whatever the energy that is left out, so this is spool 1 is going to be harvested using a low pressure turbine, a different spool, which means that when you drive these components at different speed, it is better for internal aerodynamics because you can streamline the flow according to the design specifications of each component. Otherwise, everything, if it's going to be coupled, then you can't optimize the aerodynamic characteristics, internal aerodynamic characteristics of it. So here is the second spool from which you run the fan. The configuration is very similar to what we have done before. But then it is enclosed in a duct. Then this is a nozzle here. So you're able to appreciate it now here. So here is the unperturbed free stream condition. This is the inlet lip, is the frontal face of the fan, 2. This is the exit of the compressor, 3. This is the exit of the burner, 4. And this is the exit of the turbine. This is the exit of the nozzle, 9. So here, this you can have it as 4.5. Here it is 6. I'll put the word here mix M because the bypassed air will mix at this particular point. Now let's go through this configuration here. So the air is drawn. The air is drawn into this engine. Is drawn into the engine. So here the purple part also is there. This is the total amount of air that is drawn, but only the purple part is bypassed here. Now let's come back to the bypass bit later here. So this core will pass through the high pressure compressor, pressurized, burn with the fuel, mixed with the air and fuel will mix, and then it will burn. Then you have this high pressure turbine and the low pressure turbine, and then it will come here to the mixing chamber before it expands out. Simultaneously, now you can see this, the bypassed air will be passing through the outer core of the central core of the engine, outer surface of the, this is the central core of the engine here. So this is going to pass through. Now what is going to happen is that because of this high temperature, this is going to give off heat. So as the purple part of the air, what you see here, the bypassed air passes through, the temperature increases by gaining heat from the actual combustion process. You're recovering heat here. Then it will go in and it will start to mix with the central core of it, what you see here. And then it is coming out as one nozzle, one jet mixed with hot and cold. So now you can see that's the reason why I call mixed exhaust stream configuration. Okay, so this is the mixed exhaust stream configuration. So let's try, understood all of this. The critical element of this is that the pressure must be perfectly matched. If there is unmatched in pressure, then there will be a reversal of the flow, and that will damage the fan blades and it will bring the flight down. So that's the reason why you can't operate this at very high bypass. You can operate this very low bypass because you want to make sure that the pressure in the mixing zone and the flow streams are perfectly matched so that there's no reversal of the flow taking place. So pressure scheduling is very important. let's look at the enthalpy entropy diagram. So this is the unperturbed free stream conditions P0. This is flight static state H0. In the inlet, it is being pressurized in the inlet PT2 T2, which is further being pressurized in the fan P13 T13. Then you have the core flow entering into the high pressure compressor to T3. Here it is pressure PT3. Then you have the combustion taking place, the combustor T4. Here is the pressure PT4. Then expansion taking place in the high pressure turbine. Then expanding further in the low pressure turbine. Let me stop there at this particular point. So here is this high pressure turbine, then it's a low pressure turbine. In the meantime, that air which was also passing through the inlet, which was inlet, this is the fan, and that is bypassed, will gain its temperature as it passes through. So the temperature increases here as it passes through, and then eventually somewhere here, when you talk about the mixing here, it is a combination of the purple and yellow. So it is here, it's a hot and cold. So this temperature will also give off heat, the mixing taking place. So somewhere here, that will be the place where you have the 6M mixing. And from here, it will expand in the nozzle. So this pressure difference is very, that bar is very important. Otherwise, you'll have a reversal flow taking place. Understood, all of you? Okay, so now let's go back to the PowerPoints here, what we have seen. Turbofan was basically invented the way to reduce the waste, recovering the waste. Most of the commercial and military aircraft are powered by turbofan. So here is this turbojet. Here is the modification like what we have seen. I use this low pressure turbine to drive the low pressure fan, and that's what we have seen there. And this is the bypass duct, what you see here. So here you can see there's a portion of air enters the core of the engine, and the rest of air is bypassed, flow around the outside of core of the engine in a bypass duct. So what you see here. So bypassed air is ejected as a cold jet around the engine, which is unmixed exhaust fan, or sometimes it could be mixed with hot core gas before it's ejected into the core fan. So we looked at the two configurations here. So So the objective of bypass system is to increase thrust without increasing fuel consumption. That's the main advantage of it. This is achieved by increasing total air mass flow, but there is no need to burn fuel to heat bypassed air. This also makes turbofan engine quieter and produce more thrust at low speed than turbojet engine. So here you see this diagram, what I have already explained here. So here is this fan expansion. This is the nozzle expansion here. This is the unmixed air bypass. So here is a bypass ratio. So here is the mixed bypass, mixed exhaust bypass turbofan engine. Bypassed air is mixed with hot core gas in the mixing chamber and ejected out to the same core nozzle. The static pressure of the hot and cold streams where they mix should be same, otherwise there will be a backflow reversal flow, which is not a desired phenomena here, which could damage the blades. There should not be significant pressure difference between either stream. Engine back pressure affects the mass flow and the fan pressure ratio. Therefore, fan pressure ratio, this fan pressure ratio pi f and the bypass ratio alpha are not independent of one another because of the said reasons, because otherwise you'll have the backflow. So engines are designed in such a way that the velocities of two streams to be as close as possible and the total pressure difference between the streams are minimal. And this is the cycle diagram, which now you'll be able to understand much better because we have done it in the other one. Okay, so now let's look at the third configuration, which is a turboprop engine. So we already looked at the turbojet engine, improved it to have an afterburner, thrust augmentation. We looked at the cycle diagrams. We looked at the development of a simple turbojet for improving the fuel consumption by recovering the waste in a turbofan engine in two configurations. One is the unmixed, other one is the mixed configuration. Now the third configuration is a turboprop engine. Now turboprop engine, they can't fly at very high altitude because it has a propeller. Because it is having a propeller, one of the common things is there is a critical speed up to which you can operate the propellers, otherwise you will end up in having a wingtip vortices, which will result in the formation of shock waves, which is not a desirable one. Okay, it will affect all the drag will always affect the engine performance. Turboprops are essentially a jet engine attached to a propeller. So the principal configuration is same. You recover the waste. After the generator, gas generator, that energy is used to be recovered in a low pressure turbine or a power turbine. This is used to drive the propeller. Where we used to drive a fan, now that entire configuration is used to drive the propeller. Compared to turbojet, turboprop have better propulsive efficiency at lower flight speeds because it is able to accelerate a larger air flow through a small velocity range. Because you can see that the area is much larger through which it can swallow the air even at low speeds. Again, they are of two configurations. One is a coupled power turbine, which is not a very aerodynamically streamlined, which means coupled means everything is being driven by one shaft, where the turboprops are propeller and compressor linked by a single shaft driven by a multi-stage turbine. But the more advanced version is a free power turbine. The compressor and propeller are driven by separate mechanically driven turbines. Okay, so the free power turbine, this is the power turbine or the low pressure turbine, that is designed to drive the propeller. And here the high pressure turbine is used to drive the high pressure compressor. So they are aerodynamically streamlined. So the stock from the low pressure turbine is used to drive the propeller, propel the core gas turbine will rotate at different. So now they operate at different speeds, which basically is to having a good aerodynamic streamline of the flow inside the engine component. Now the limitation is that you can operate it at low speed, you can't operate it at high speeds, which means you can't fly at high altitudes. Also there are losses, tip vortex. But the developments have taken place is to go with the smaller size propellers, but then go for more number of propellers, because these are much bigger propellers. Then if you have a smaller propeller, then have more number of propeller blades. So modern turboprop engines equipped with propellers that have a smaller diameter but larger number of blades for efficient operation at much higher flight speeds. Now these are called prop fans. Now again, the problem of tip vortex is still there. Even for this tip vortex is still there, losses. To avoid that, the tip of the blade is twisted like a smitter sword. Yeah, let's twist it so that you can minimize the tip vortex. So you can see that swept back leading edge, just like how you have in A320, the wings will have a winglet. Have you seen this one? Wings will have a winglet. That's to minimize again the tip vortex losses there. Okay. So here in propellers, you have this swept back arrangement to minimize the tip vortex. So here you see this turboprop and prop fan aircrafts. So this is a turboprop, and here these are the prop fans. Now again you can see that the inlet so here you can see this, the inlet size, this is the inlet, is much smaller. You don't need a huge size of the inlet, because we are just going to use only 10 to 20% or 25% of the air flow through this inlet to produce this thrust, because nearly 80% of the thrust is going to come from the propeller. So which means it is very fuel efficient, but it can fly at low altitudes. So that is what we see here. The turboprop engines, normally 10 to 25% of thrust is obtained from propulsive nozzles, which is the main core nozzle. The remaining is going to come from the propeller. So again, the turboprop engine has two thrust components, one by the propeller, other one is by the momentum produced by the exhaust gas flowing out of the nozzle. Now this power sharing, because is to be designed in the production stage itself, because the size, everything, and the dimensions of this one has to be taken into consideration during design stage itself. You can't just do it at the end. So the power sharing between the propeller and the jet is a decision made at the design stage of the engine for a given operating condition. The cycle diagram is very simple. So here you have this compression, combustor, turbine, and nozzle. Since we have gone through it before, so we will now move to the last configuration, which is a turboshaft engine. Turboshaft engine, it's not a jet engine at all. It's a shaft. There's no jet. All the power that is produced is converted as a shaft power. And then if you have a worm gear arrangement here, and then if you drive a blade, then it becomes a helicopter. So turboshafts are mainly used for driving helicopter rotor instead of a propeller. Now almost all aircrafts will have turboshaft engines, which is an auxiliary power unit that is used to generate the electricity and other auxiliary air supplies in the aircraft. So helicopter engines are generally designed so that the speed of the rotor is independent of the spool rating speed inside the core of the gas generator. So which means that here you have this this is the low pressure turbine. This low pressure turbine is used to drive this shaft, and here this high pressure turbine is used to drive this high pressure compressor. So you can have an independent rotational speed of it, and also you could also try to make some gear arrangements so that you can keep the speed of the spool constant while you can vary the speed of the shaft, rotor speed. So here you see this configuration. There is no ramming effect because it's running at very low speed. All that you need is to have a streamlined flow of air entering into it. It's almost like a bell mouth entry into it. And here you have this reverse flow combustor. Flow comes back and then it mixes with the fuel, burns, and then all that flow that is expanding is produced as a shaft 1, which is then used to drive the rotor. There is no jet that is going to be used to produce the thrust in turboshaft engines. So the turboshaft helicopter engine uses shaft power to generate thrust from spinning rotor blades. No jet is produced by expanding the exhaust gases through the nozzle. Turboprop engine uses shaft power to drive the propeller, which generates most of the thrust. However, a small fraction of jet thrust is produced by exhaust gases expanding through the nozzle, but that is very minimum, negligible. So here you see this comparison of what of the architectures what we have studied. So we looked at the turbojet, simple turbojet, and simple turbojet with an afterburner. We looked at an turbofan, unmixed exhaust turbofan. We looked at the mixed exhaust turbofan. We looked at the turboprop engine. We also looked at the turboshaft engine. So each configuration has its own advantages. Turbojet is simple in its design. They also has disadvantages. They are not very fuel efficient. Turbofan is a development of the turbojet, so it becomes quieter, better fuel efficient. Again, it has a larger frontal diameter, so there are also the advantages and disadvantages, which means the ram drag increases. So here it is outweighing the advantages and disadvantages of it. Okay. So the next, for the course, we will be spending a bit more time on this arrangement, which is what you see here is a ramjet engine. So far what we have seen is a gas turbine based propulsion system which had rotary components, which had a compressor and a turbine. Now when we go for very high speed applications where ramming effect is taking over and building up the pressure, of course this is still the configuration is similar. You have an inlet, you have a combustor, you have a nozzle. The pressure build-up is through the inlet system, which doesn't have any rotary component, and instead you have a lot of shock waves in it. We will be covering those things tomorrow, but then the combustion is taking place here in the combustor, and here is the expansion taking place in the nozzle. Now the configuration designs are different for ramjet and scramjet. So in the ramjet you see it's a convergent divergent inlet, and the nozzle is a convergent divergent nozzle. But if you look at the scramjet, you have just a convergent inlet and just a divergent inlet, because the reason is here we want the combustion to take place under subsonic conditions. We want to make sure here the Mach is equal to less than 1. Now that is taken care of by the shock train configurations, which we will discuss tomorrow. So though it is flying at Mach 3 to Mach 5, when it comes to the combustor, it is subsonic combustion taking place because the air enters into the combustor at m less than 1. So the combustion combustor burn gases leaving the combustor is still subsonic, so you need to accelerate it. So you have a convergent m equal to 1, and then you have the divergent geometry. That is the arrangement what you have. You have no rotary components here. When it comes to ramjet propulsion, we'll be discussing these details later. At the entry into the combustor, we are not decelerating it to subsonic, it's still supersonic. At the end of combustion, m is supersonic. If we can't have a convergent geometry, which will reduce the flow, we wanted to accelerate it, so that's why we have only the divergent geometry. Okay. So anyhow, we will be looking at these things with detail. I just wanted to cover this also. Gas turbine engine propulsion and hypersonic engine propulsion. The commonality is that it also has an inlet as a gas turbine engine inlet, and then it also has a combustor. Combustion can take place either at subsonic or supersonic conditions. If it's a scramjet, it is supersonic combustion, m greater than 1. If it's ramjet, m less than 1. And then you have the turbine or the nozzle system for this hypersonic propulsion applications. So I think with this we can conclude this morning's lecture, and then after our lunch we can start with the next topic that will be on the combustion theory. Okay.
They have any doubts or anything?
Yeah.
Anything you want to ask?
Sir, what is the typical pressure ratio of P0 and P9? Because both are in the, that means the entry point P0 and the extreme out is the P9. So what is the typical pressure ratio between?
Yeah. So that is from the nozzle point of view, which let me explain this a bit more at this particular point. So just like how I explained that the inlet is adiabatic, okay, the nozzle is also adiabatic. I mentioned it here. Nozzle is also adiabatic here, which means that the total temperature at this point remains constant, total energy, which means enthalpy HT5 is equal to HT9. HT9, which is again coming to the question what you asked here. So this is the temperature T9. The total temperature is TT9, and the pressure is P9. The total pressure is PT9. So if it is going this isentropic process between P9 and this is the, or in other words, what I'm trying to do is, this is P9. The question what you asked, what's the difference between P9 and P0, yeah? If I place a pitot static probe here, I will be able to measure PT9, stagnation pressure. Understood?
Yeah.
Okay. So that will be the stagnation pressure here. Now, this ratio from here to here is nozzle pressure, no, this pressure from here. The nozzle pressure ratio is PT5 by P0. That's the maximum potential that is available for the nozzle to expand. And then the total pressure ratio of the nozzle is PT9 by PT5, total pressure ratio across a nozzle. And this nozzle will have an adiabatic efficiency of the nozzle. Okay. Now, the question what you asked is very important, because that defines what kind of flow that is coming out. Okay, so if P9 is less than P0, it is underexpanded. Sorry, it is overexpanded. If P9 is greater than P0, it is overexpanded. So this is the check what we'll be doing later on, P9 and P0. So if the difference is there, then it could be either underexpanded or overexpanded. Depending on that, the flow structure coming out of the nozzle will be different. So if you look at the adiabatic efficiency of the nozzle, which in fact it is dependent on the nozzle pressure ratio, and then P9 by P0 power gamma minus 1 by gamma minus 1 by pi n power gamma minus 1 by gamma divided by nozzle pressure ratio into P9 by P0 power gamma minus 1 by gamma minus 1. This is the efficiency of the nozzle. So that's what you see, that the nozzle terms, this term, the efficiency of nozzle, and then P9 and P0 plays an important role. If P9 is equal to P0, then it is perfectly expanded. But to make it perfectly expanded, most of the modern applications are coming with a variable area geometry nozzle, which means you can vary the area so that you can adjust this to have P9 equal to P0, which is the optimum design configurations.
But that is also difficult because P0 is also changing constantly
Yeah.
with the height.
Yeah.
So
Yeah. So depending on the environmental at which it is flying, as you say, we may end up in a situation where it could be either overexpanded condition or underexpanded conditions. Depending on that, the flow structure, the shock diamonds that is being formed will be different. Yeah, I think we'll be discussing that on Wednesday, day after tomorrow. We'll be looking at this aspect, P9 and P0.
And another question is, already you have told that during this turbofan in mixed conditions, the velocity or pressure of the bypass air and the combustion air which is coming from the nozzle. So if these two are not exactly same, so either it will backflow the bypass air or it will be creating a obstacle to the nozzle exhaust. So especially again the same questions, if P0 is constantly varying, so how these two are exactly matching? It is a totally a design concept or some control system is there? Because even a small deviations in the pressure there, if the two pressure, it will either backflow or it will restrict the outlet pressure of the nozzle, outlet flow of the nozzle.
Yeah,
it's very critical actually, I think.
Through one of my student projects, we did this simulation for this condition. There is a limit. It's up to which, a small limit up to which you can operate it.
Okay.
But primarily it is design features, the fan bypass ratio, and the so fan pressure ratio and the bypass ratio, they have to be matched. If they are matched, then the surrounding conditions varying, that affect.
Yeah, because if P0 is changing, so accordingly the bypass air pressure is also change, and also the total combustion pressure will also change.
Yeah, but that is being taken into consideration with the design aspects of the fan pressure ratio and the bypass ratio. Yeah.
That means that bypass ratio is also constantly varying. It is not a fixed.
Bypass ratio is the mass of air that is being
that I
bypassed.
understand. But that is also varying. That means depending on the conditions.
It
depending
is the mass we're looking at it.
Okay.
Only if the density variations are affected due to the pressure,
Okay.
because temperature is also another factor there. Mass is rho a v there.
Okay.
But of course, this is a very complex phenomenon,
Yeah.
as you said. Yeah.
Okay. Yeah. Thank you.
What is the typical pressure inside the combustion chamber?
It depends on what's the pressure ratio of the compressor. Yeah, so for example, if a pressure ratio of the compressor is 40, so around that range, in 40 bar or something like that. If it's a pressure ratio is 4, it's about 4-5 bar will be the combustor pressure ratio. Combustion takes place at constant pressure, so the temperature alone increases, but there will be some pressure loss in the combustor. So depending on the sizing aspects, the pressure of the combustor will be different. There is one more question there.
So we discussed the mixed exhaust case of a bypass flow in a turbo fan, right? Is there any case where we can actually inject some fuel into that heated air and create extra thrust? Similar to how we do in an afterburner, but then with the bypassed air.
Again, this comes to the same point what I was saying, the matching of the pressure is very important. So it is just recovering the heat from the core of the engine, not any additional, because you don't want it to inject any additional. See, when you inject fuel, it is coming out as CO2, that's all. The whole idea is to reduce the carbon which you inject into it, fuel into it. The more fuel injected, it's more coming out as CO2 emissions. So ideally, it is just recovering the waste heat.